All right, so new topic today. So doing chapter 8. I am going to do chapter 8 in a slightly different order than, well, what's in the book. So we're going to do 8.1 today, and then I've got a video that I will want you to watch before Wednesday, and that'll be stuff from 8.4. And because it's kind of the whole point of, at least in my mind, it's the kind of the whole point of doing stuff with linear transformations. And then we'll go back and catch 8.2 and 8.3 and integrate how we can use the stuff we learned in 8.4 to help us find to answer the questions that it asks us about in 8.2 and 8.3. I personally think it's a better order to do it in, so that's the way I'm going to go. All right, so this is section 8.1, talking about linear transformations. So just write down the definition here real quick. So we say that a transformation from one vector space to another. So in this case, I've got my function notation here where I've got t is describing a function. T is the name of the function. V is the domain of the function. W is the codomain of the function. Both of those are going to be vector spaces for our purposes now. And we say it's a linear transformation if whenever you take two vectors, I think the book uses u and v, so I'll go ahead and use the same letters. Whenever you take two vectors u and v, in v, and any scalar, any real scalar, then these two properties have to hold. The first one is that if I apply the transformation to the sum of the two vectors, the transformation breaks up over the sum. And then the second one is that if I take the transformation of a scalar times the vector, I can move the scalar out in front. So I mentioned this on the video for today as well, but I want to mention it here because this, from an algebraic perspective, the big deal behind linear transformations is that there's structure here preserved. So we remember talking about addition and scalar multiplication generally for vector spaces back in chapter 5. Those we remember that those particular vector spaces, it's possible that the addition and the scalar multiplication are defined in ways that aren't standard. We saw weird ways where we could define addition, weird ways we could define scalar multiplication, but it still satisfied those vector space axioms. So what the definition here for linear transformation says is that this linear transformation has to be well behaved with respect to those operations. So notice that this plus sign here, this is addition in V, whereas this plus sign here is addition in W. So what I mean by behave nicely is that it has to preserve that additive structure between the two spaces. And then the second part here, same idea, this scalar multiplication here takes place in V, this scalar multiplication here takes place in W. So again, that scalar multiplication structure has to be preserved by the function t. One definition I did not mention on the video, so I'll mention it now, is that if your function maps v to itself, if your function maps v to itself, we refer to this as a linear operator. It's just a special name describing the fact that the domain and the codomain are the same here. So if you see the word operator, it still just means linear transformation. It's just that we've specified that the codomain has to be the same thing as the domain. All right, so let's do some examples here. Let's look at this first one. So we've got this function going from the reals to the reals. Going from R3 to R3. So going from three-dimensional Euclidean space to itself. So this is an example here that if this turns out to be a linear transformation, then this will be a linear operator because the domain and the codomain here are the same. So this is how it defines the transformation. So it takes a vector x, y, z, and it maps it to those three coordinates. So if we're going to show that this really is a linear transformation, then we need to show a couple of things. We need to show that if I take the transformation applied to the sum of two things, then I have to be able to break up the transformation, oops, it's a y, over the sum. So if I take the transformation applied to the sum of the two vectors, that's the same as the sum of the transformation applied to each individual vector. That's one property we have to show. The second one, of course, is the scalar idea. So we have to show that we can pull the scalar basically out in front. And this, much like what we did for the vector space axioms and for the inner product space axioms, this generally just involves plugging in on one side, plugging in on the other side, and making sure you actually get the same answer both times. So when we do this, if we do the first one, well, we get x1 plus x2 in the first component. We get y1 plus y2 in the second component, and z1 plus z2 in the third component. So notice I'm adding the vectors first before we apply the transformation. And now I just need to plug this in to the transformation, so I'll get 7 times the x1 plus x2, 2 times the y1 plus y2, minus 8 times the z1 plus z2. That's the first component. Do the second one. I don't know if I can get things to scroll so I have a little bit more room. And then do the third component. And then, in this particular case, it's probably just as easy to split it back apart now as it is to plug it in on the other side. Notice that I can distribute each of those constants through and then rearrange some things. So in this first one, I can write this as 7x1 plus 2y1 minus 8z1, and then 7x2, 2y2, 8z2, with the appropriate pluses and minuses in there. Same idea with the second component. Oops, that's a minus. And same idea with the third component. And then we should notice here that we can split this up. Let's see if I can do this in a different color. Split this up at the individual, oops, wrong spot. Individual, I'll call them plus signs, even though that second one there is a minus. But we can split that up at those places as what? We can do 7x1 plus 2y1 minus 8z1, and then comma, negative y1 plus 5z1, comma, 4x1 plus 7y1 minus z1, and then plus the other piece with just x2s, y2s, and z2s plugged in rather than 1s. And then hopefully now we recognize that this is t of x1, y1, z1 plus t of x2, y2, z2. Not a huge surprise, since I said that this was going to be an example of a linear transformation, that this turned out to be true. Now, before I do the second part won't take as long because there's not as many things to write. But before I go do this, notice that if I think of this as a different set of coordinates, if I think of this as, say, a u, a v, and a w, if I think of the outputs as a different set of coordinates, a u, v, w, rather than an x, y, z, notice that you can write these equations as 7x plus 2y minus 8z, that's what u is equal to. V is negative y plus 5z, that's what and then the w is equal to 4x plus 7y minus z. Notice that's the set of linear equations. So there's another place where we get the name linear transformation, is that when you do these for Euclidean spaces, the new set of coordinates need to be linear equations in terms of the old set of coordinates. So what I mean here is the u, the v, and w are linear equations of the x, y, and z. Notice there's no constant put on the end here. It's just x, y, and z. So they're just the linear equations here. That's another reason why we have that name for linear transformation. And that's always the case for ones that are Euclidean space to Euclidean space. They all have to be linear equations like this, and we're going to see where that's going to help us write the transformation in a special form here in a little bit. All right, let's do the second part. I know it's tedious, but still need to kind of go through it, illustrating the ideas here. All right, so again, if I want to do this one, first thing I want to do, is write down the wrong thing, apparently. First thing I want to do is distribute that c through the vector. So doing the scalar multiplication. And then plug this in. Not t of. The first coordinate is 7x1, 7cx1 plus 2y1 minus 8cz1. So just putting cx1 and cy1 and cz1 in for u up there, if you will. Second component will be negative cy1 plus 5cz1. Last component will be 4cx1 plus 7cy1 minus cz1. And this, now hopefully you can see why we need those linear equations, at least for the transformations from Euclidean space to Euclidean space. I need to be able to factor out those c's to be able to get the second condition to be correct. And if I have something that's not linear, I'm not going to be able to factor out a c. Like, for example, if one of the variables was squared, I would have had a c squared in there, and so I don't have just a c that would pop out. If I had a constant added on the end, there wouldn't be a c attached to it. I wouldn't be able to factor the c out. So hopefully you can see a little bit more why we need those linear equations in here for it to be a linear transformation. So this is C times the mess. Which really is the constant times the transformation. So we really do see here that we have a linear transformation. Any questions on that one?
You didn't have to include the subscripted one, did you?
I did not have to do it. I only included the subscripted one there because I had talked about the two vectors to start with, and the first one had a 1 in it. You can just write it as x, y, z if you'd like. Yes, that's fine. The important part is that you're using an arbitrary vector. I don't really care if you use x, y's, and z's as long as you have 3 different symbols. All right, let's look at the next one here. This one hopefully won't take as long. The next two shouldn't take as long. All right, so this one is defining a transformation from Euclidean space Rn to the real numbers. So this one, 2 different spaces. And we're going to define our transformation by doing the dot product where we pick a fixed y. So the y is not going to change. We're going to let the x change, but not the y. So again, if I start with, say, 2 vectors, let's call them x1 and x2, and do the sum of those 2 things. I'm not going to write, I don't need to write out a whole bunch of symbols here because it just says I'm going to do the dot product of this sum with y, and I'm using the dot here rather than our inner product symbols because we're doing the usual inner product on real vectors here. So typically we refer to that as the dot product and use the dot. Then we know that dot products distribute nicely over sums, and that's exactly, each piece is exactly how the transformation is defined. For the oops, I forgot my C. For the second one, we just need to see that a constant pulls out. Well, according to the definition of the transformation, I would have Cx dotted with y. But we know from our properties of the dot product that constants pull out of that as well. So I would now have C times the transformation applied to x. So this is a linear transformation. Like I said, that one was much shorter. Questions on that one at all? Next one's not bad either. Oops, except I made a typo. This should be a T, not a C. The transformation is T. All right, so remember this notation is continuous functions on the interval from A to B. So our transformation T here is defined from continuous functions to the reals as the integral of the function from A to B. So again, if I have 2 functions, I want to show that the transformation breaks up over sums, and this is just going to be a little bit of calculus review, essentially. So the transformation says to put in the sum in for the integrand, and then from what we know from calculus, the integral breaks up nicely over the sum. And that, of course, then is the transformation applied to the 2 functions individually. Like I said, this is more of a calculus review than anything else. The transformation now applied to a constant times a function is, well, as this says, to put the constant times the function in for the integrand. That's how the transformation is defined. We know from calculus that we can pop that constant out in front. And then, of course, that's just the constant times the transformation. And you probably know that other calculus types of operations will give you linear transformations. Differentiation would be a linear transformation. Limits, as long as the limit exists for the function, limits would be linear transformations. Anything that you can break up over sums and pull constants out of, those are going to be linear transformations for anything that you've dealt with before. Any question on this one or the previous one? All right. Okay. Well, let's look at something that's not transformation. So let's look at this first one. This first one says, if I take some inner product space and map a vector to its magnitude, is that going to be a linear transformation? Well, this one actually has a couple of problems with it. Let's do the scalar multiple first. If I did the scalar multiple, that would say do the magnitude of the scalar times the vector. And then remember from work that we did back in the inner product space chapter, if I pull a constant out, an absolute value goes with it. So this is not equal to a constant times the transformation if the constant's negative in this case. So right away that tells me this is not an inner product, or excuse me, this is not a linear transformation. We also know that in general, if I do a sum of two vectors and take its magnitude, in general, this is only just less than or equal to the sum of the magnitudes. That's the triangle inequality. Remember that as well. So in general, when I apply the transformation to the sum, I don't get the sum of the transformations. So in this case, neither of the properties are going to hold in general. There will be cases where they do, but in general they don't. A similar idea pops up here in the next example, where we take square matrices and map them to the real numbers through the determinant function. Well, we know in general that if I do the constant multiple again, if I do a constant times a, I think this was on your last test as a matter of fact, if we try to pop this constant out in front, the c doesn't just come out. I have to pop out a c of every single row. Right? Yeah. One comes when we take the c out of the determinant, we do that by every row. A constant times a row changes the determinant by that constant. Well, the constant times the scalar multiple of a multiplies every single row by c. So again, in general, the transformation of the constant times the matrix will not be the constant times the transformation. And we also know that in general, we cannot break up determinants over sums. So we also get that the sum doesn't work. So this is definitely not a transformation. Any question about either of those two? Oh, I messed that up. I got another typo here. Apparently I was not careful when I was typing this stuff up. This doesn't even make any sense with the transpose. I better flip my subscripts. Transformation from mn to n, m sub mn to n sub nm. I better flip my transcript. If for this to even be defined, I got to make sure I'm in the right spot. Is this a linear transformation? Well, let's test it out in this case. The transformation says take the transpose of the matrix. That's takes the transpose of the input. We know from work we've done previously that transposes distribute over sums. So individually, then we have the transpose of each matrix. So at least the additive property here holds. For scalar multiplication, we plug the input and take the transpose of it. So we need the transpose of a constant times a matrix. Well, again, from work that we've done previously this semester, we know that the constant pops out, and that'll be the constant times the transformation then. So this is a linear transformation in this case. All right, let's think about this last one for a second. Remember the p sub n, in this case, so p sub 3, is just polynomials of degree 3 or less, along with the 0 polynomial. And we're going to define it by what looks like a shift, right? This would be, if you think about it in terms of graphically, this would shift the polynomial up 1. Is this going to be a linear transformation? Well, I think we're going to run into issues right away with trying to do this for the sum of two polynomials. This would say take the input, which is p of x plus q of x, and add 1 on the end, right? That's what the formula says to do. You take the input and plug 1 on the end. If we apply the transformation individually, however, we would have the p of x plus 1 plus the q of x plus 1. And these two certainly are not the same thing. So these are not equal in this case. So this is not a linear transformation. So you have to be a little bit careful. A lot of times when you think of linear functions meaning straight lines when you graph them, you allow that plus b on the end, right? Because you think of the slope-intercept form of y equals mx plus b. That's a linear function. But for linear transformation, that shifting part, that plus b part, if you will, is not allowed. Okay? Because it doesn't give you that structure saving thing of having the addition being first or second. Question on any of those at all? All right, so let's talk a little bit about how we can get matrices of a linear transformation, because that's actually the next topic that we're going to talk about. That's what section 8.4 is about, for doing this for any transformation, not just ones that are Euclidean. And so the idea, yes?
Could you scroll back up for just a second? I just need to finish copying.
Oh, I'm sorry.
Oh, no, that's okay. I'm almost done.
No worries. Sorry about that. It's hard to know when people are done writing when I can't see you writing.
Yeah. Okay, I'm good now.
Oh, cool. Thanks for telling me.
You're welcome.
All right. So we want to try to take advantage of basically matrix multiplication properties to get these answers. So again, we think of this as, let's think about where this is going from. So in this case, your domain is R2. And I know it's R2 because it's just an X and a Y. And it goes to R3 because I have a U, a V, and a W again. So let's think of these as U, V, and W. So like I wrote before, I can write these as a set of linear equations. I can write U equals negative 2y. I can write V equals 3x. And I can write W as x minus 2y. And again, going back to work we've done earlier this semester, we know how to rewrite this system as a matrix equation rather than a set of linear equations. So we know that our input is the x and the y. We know that the output is the u, the v, and the w. So to make the multiplication work here, I better have a matrix in front that has 3 rows because I've got 3 rows in my output, and I better have 2 columns because I have 2 columns in my input. And then we know that we can just write the numbers across to make this work. So in the first row we would have 0 and negative 2, because again when we take the 0 times the x and the minus 2 times the y, I better get the u. In the second row we would have the 3 and the 0, and in the third row this would be the 1 and the negative 2. So notice all I'm doing here is just rewriting our vectors as columns rather than this coordinate vector, if you will, and then rewriting our linear equations as matrix multiplication. And then I can see where the equations are coming from, right? They're just coming from right here, and I'm just writing the numbers across the rows. So this, sometimes you will see, well, a lot of times the book will just call it A. So when you write it this way, if A is this matrix, and I better say, let me give us dimensions here, if I can erase. Let's say it's an n by n matrix, then T sub A goes from Rn to Rm. So notice it flips things around here, right? The codomain space had dimension 3, and there were 3 rows. The domain space had dimension 2, there were 2 columns. So it flips things around. We define this T sub A transformation as T sub A of x is just the A times the x. I should write it is defined as. Forgot a couple of words in there. The book, well, the stuff that this stuff is back in chapter 4. I do all the linear transformation stuff all at the same time. That's why I didn't cover chapter 4 first, because it's all the same stuff. So I just do it all at the same time. But usually they'll just use an A for that. We'll have a slightly different notation for matrices of a transformation when we get to section 4. Okay, so let's look at the second one. The first thing we notice is that the transformation goes from R4, because there are 4 inputs, to R3, because there are 3 outputs. Okay, so this tells us that the matrix for the transformation is going to be 3 by 4. It inverts the dimensions, if you will. It makes sense if you think about why that has to be true. Your inputs are 4-dimensional vectors, which means there have to be 4 columns to your matrix to make the matrix multiplication work. So it better invert them. All right, so in this case then, we have a 3 by 4, and then we can just write the numbers across. So in the first row, if looking at the first component, I better have 7, 2, -1, 1. In the second row, we better have 0, 1, 1, 0. And in the third row, we better have -1, 0, 0, 0. And then you can write your transformation then as matrix multiplication. So your T of x here will be this A times x1, x2, x3, x4. Question on that one at all? All right, so let's do a couple more that actually make us think a little bit about geometry here. So the first one says that we're going to do, that's not the right word. I mean onto the xy plane. Jeez Louise, I should have paid more attention when I was typing this. If I was defining it if I were doing projection onto the y-axis, it would just be to r, not to r2. So if I'm going to project it to the xy, if I'm going to go to r2, I better go to one of the coordinate planes. So let's just do xy plane. Okay, so let's think about the geometry behind this. So here's R3, and I have some point up here, x, y, z. What we mean by projection onto the xy plane, we mean we're going to drop this down perpendicularly to the xy plane. That's all we mean by projection to the xy plane. I could have drawn it as vectors, but I think it just gets more confusing with the vectors actually drawn in there. So the coordinates at this point, then, if I'm projecting down to the xy plane, the z-coordinate is 0, and I didn't move left or right or front or back. So the output is just xy 0. So that tells me my transformation here in terms of the symbols are just xy 0. So xyz goes to xy 0. That's projection onto the xy plane. So the problem in this case asks us to find the matrix of this transformation. Well, I can still write out the rows like we did previously. This is going from R3 to R2. Whoops. Sorry. It says from R3 to R2. If I'm going to go from R3 to R2, I'm not actually putting in this last component here. The point goes to xy 0, and then I just think about the xy plane as ignoring the z coordinate. So really, I just mean xy. So if I'm going from R3 to R2, then I'm going to have a 2 by 3 matrix. The first component is going to be what? Well, there's 1x, no y's, and no z's. And the second component will be no x, 1y, no z's. And you'll notice that if you take this a times x, y, z, all you get is xy. I apologize for the slight goof up there. All right, one more geometric one here. Reflection about the line y equals -x. All right, so I've got to draw my picture pretty carefully here. Here is your y equals -x line. here's my xy. If I'm going to do reflection across the line y equals x, that means I got to go basically perpendicular here and then go down the same distance here. And if you go through the geometry and think about it, this has to be the point negative y, negative x. Getting flipped around the line y equals negative x. It's going to flip both your coordinates. So your transformation here will be negative y, negative x. So our matrix here, the x is going to this component, so that'll be 0 and negative 1 for that first row, and the second row will be negative 1 and 0. Questions about this at all? Okay. Well, let's go to the next one here. What do we got next? Dealing with linear transformation and bases. This is a big deal. This comes up in the next section. All right. So, how can we figure out the output for an arbitrary x if we already know what the basis is? That's the idea behind this one. So certainly we know that if we have a basis, then we know we can write x as c1v1 plus c2v2 plus cnvn. That's the whole idea behind the basis, right? Being able to write it as a linear combination of the basis vectors. Well then, if I just plug in that linear combination into the transformation, then by the properties of the transformation, I know that I can split the transformation up over the sum and pull the constants out. So what this tells me is, the whole point of this exercise is that if we know what the transformation does to a basis, then we know the entire transformation. So we know the output t of x for any x. So the whole point of this is that if you know what the transformation does to the basis, then you know what the transformation does, period. Okay? So let's look at an example here, and it's probably the last example I'm going to have time for, given the time. So let's look at this one. So we know we've got v1 is the vector negative 2, 1, and v2 is the vector 1, 3. It's easy to see, hopefully, that v1, v2 forms a basis for R2. They are certainly linearly independent, because remember that if you have a set of two vectors, they're linearly independent if they're not scalar multiples of each other, and certainly those two vectors are not scalar multiples of each other. So then this one tells you that t of v1 is this vector and t of v2 is that vector. It asks us to find a rule for t of xy, and then find t of 2 comma negative 3. All right, so the idea here, of course, to be able to find a rule for t of xy will be that if I have some x comma y, arbitrary x comma y, I need to be able to write that as a linear combination of the two basis vectors. So I need to be able to write the xy as a c1 and a c2. So this would tell me that the x would have to be negative 2c1 plus c2, and the y would have to be c1 plus 3c3, c2, sorry. Had a little 3 happy there, seeing the 3. So again, just to go back here, because I think I went through it a little quickly. This is some arbitrary vector in R2. This is trying to figure out how, if I have an arbitrary vector in R2, how would I express it as a linear combination of my bases? So what that means here is that I need to solve for C1 and C2 in terms of xy. Probably the easiest way to do that, at least in my mind, would be think about the matrix equation So write it as a matrix equation, and then I want to get C1 and C2 by itself, which would mean that I would need to take the inverse of this matrix on the left-hand side. To get the C1 and C2 by themselves, I would need to be able to do the inverse of that matrix. Luckily for 2 by 2 matrices, the inverse is not that hard to do. We basically use the adjoint formula for it. The determinant here is -7. So I put a -1/7 out in front. You flip the main diagonal and you negate the off diagonal. So flipping the main diagonal puts a 3 in the upper left-hand corner and a -2 down in the lower right-hand corner. And then negating the off diagonal just makes them both -1s. So now if we do the multiplication, what do we get? We get -3/7 x plus 1/7 y for the first component. And then we get 1/7 x plus 2/7 y for the second component. So that tells us that the rule that it's asking for, that t of xy, is going to be... That's interesting. What did I just do? I'm sorry, that's not the rule yet. That was my problem. I know that I know what the constants are in this case. So I know that my xy, sorry about that. I know that my xy is going to be -3/7 x plus 1/7 y times the -2, 1. And then it's plus the 1/7 x plus 2/7 y times the 1, 3. All I had found at that point was the linear combination. I hadn't found the rule yet. Okay. To find the rule, now I need to apply the linear transformation, the t of xy. Now remember, these two pieces are the constants, the C1 and the C2. So according to what we talked about for applying the transformation to a basis, those constants are going to pull out of the transformation, and I'm just going to apply the transformation to the basis vectors. So this first part that's in parentheses is representing the C1. It would get pulled out in front. Because remember, you're going to be given the numbers x and y here to start with. And then the second part, forgot my y, we'll have that constant pulled out in front and the transformation applied to 1, 3. And now you know these pieces. You know what the transformation is applied to negative 2, 1, and you know what the transformation is applied to 1, 3. So just to write that down relatively quickly. I would have that first constant multiplied by the negative 1, 2, 0, and the second constant multiplied by the 0, 3, negative 5. Or negative 3, 5, sorry. And then to figure out your rule, to just finish this off to figure out your rule, you would just combine the components now. So you would distribute your constant to each of the components and combine your vectors at that point. So I'll stop there just because we're at 9:52 now, and I know you have other things to do for other classes as well. So what I would try to do is do the next one here, making sure that you understand how to find the rule, understanding what we did here with this idea with the inverse. And I will post a solution to this as well so that you can see what to do with the inverse. And then again, for Wednesday, I would like you to watch the video that I'm going to post about finding matrices of general transformations. So I'll get that posted. I'll get that posted today. I would like you to watch that. We'll probably finish this off as well a little bit, but I want to get into section 8.4. And it's going to be helpful if you understand how we're forming the matrix in 8.4. It'll save us some time. So, any questions at all before we go? All right. Well, I will see all of you later. Have a good day, everybody.
You too.
Okay. Bye-bye.